Displaying waveforms. By the end of this lesson, you should be able to display waveforms using the CRO, solve problems based on the CRO display. An oscilloscope is connected to a microphone to display the waveform of a tuning fork. What can you say about the waveforms produced by the two tuning forks? How is frequency of a vibrating body related to the waveform traced by the CRO? The audio generator can produce different types of waveforms, and the waveforms can be traced by the CRO. Click on the Waveform selection knob to see the different waveforms. There are sine waves, square and rectangular waves, and triangle and sawtooth waveforms. What can you say about the number of complete cycles of the waveform when the frequency of the audio generator is varied? Click on the frequency knob to find out. The number of complete cycles of the waveform on the screen increases when the frequency of the audio generator increases and vice versa. What can you say about the amplitude of the waveform when the frequency of the audio generator is varied? Click on the frequency knob to find out. The amplitude of the waveform remains the same even though the frequency of the audio generator is varied. A microphone is connected to the CRO. A vibrating tuning fork is brought near the microphone. What can you say about the waveform? The tuning fork is hit harder. What can you say about the amplitudes and the number of complete cycles of the two sets of waveforms on the screens of the CRO? The amplitude of the waveform increases when the tuning fork is hit harder. However, number of complete cycles of the wave on the screen remains the same because the frequency of the waves produced by the tuning fork remains the same. The tuning fork is hit again. What can you say about the amplitude of the vibrating tuning fork after a longer period of time? The amplitude of the waveform becomes smaller, indicating that the vibration of the tuning fork is slowing down. Hence, a damped sine waveform is seen on the CRO screen. A circuit consisting of an AC power supply and a resistor are connected to a CRO. What do you see on the CRO screen? A sine waveform is seen on the screen. What happens to the waveform when a diode is placed in the circuit? Only the positive amplitudes of the sine wave is being traced by the CRO. What happens to the waveform when an arrangement consisting of 4 diodes is added to the circuit? A continuous wave of varying magnitudes is traced on the CRO screen. A student uses a CRO to study the waveform produced by an audio generator. A waveform is displayed on the screen of the CRO. At what value is the time base set at? Mouse over to the time base knob to view the reading. The time base is set to 1 millisecond per division. How will the waveform change if the time base value is doubled? Click on the time base knob to find out. As the time base value is doubled, that is, from 1 millisecond per division to 2 millisecond per division, the number of complete cycles of the wave seen on the screen is also doubled. Why? With the time base set to 1 millisecond per division, the period for one complete cycle is 8 milliseconds and represented by 8 divisions. With the time base set to 2 milliseconds per division, the period for one complete cycle is 8 milliseconds and represented by 8 milliseconds over 2 milliseconds per division equals 4 divisions. Thus, the number of complete cycles seen on the screen is doubled. How will the waveform change if the time base value is increased by 5 times? Discuss the answer with your teacher. The CRO has been reset. At what value is the time base set at? Mouse over to the time base knob to view the reading. The time base is set to 2 milliseconds per division. How will the waveform change if the time base value is reduced by half, that is, to 1 millisecond per division? Click on the time base knob to find out. As the time base value is reduced by half, that is from 2 milliseconds per division to 1 millisecond per division, the number of complete cycles of the waveform is also reduced by half, that is from 2 complete cycles to 1 complete cycle. How will the waveform change if the time base value is reduced from 2 milliseconds per division to 0.5 milliseconds per division? Click on the time base knob to find out. As the time base value is reduced from 2 milliseconds per division to 0.5 milliseconds per division, the number of complete cycles of the wave is also reduced from 2 complete cycles to a half of a cycle. How will the waveform change if the time base value is reduced from 2 milliseconds per division to 0.25 milliseconds per division? Click on the time base knob to find out. Discuss the answer with your teacher. What is the setting of the time base control? What is the setting of the Y gain control? Mouse over to the knobs to view the readings. The time base is set to 1 millisecond per division, while the Y gain knob is set to 0.1 volts per division. What is the peak voltage? The peak voltage can be calculated by multiplying the selected value of the Y gain to the number of the horizontal axis. Thus, the peak voltage is 0.4 volts. What is the period of the trace? The period T of the trace can be calculated by multiplying the selected value of the time base to the number of horizontal divisions for one complete cycle. Thus, the period is 0.008 seconds. What is the frequency of the wave displayed? Frequency is the reciprocal of period. Thus, the frequency of the wave displayed is 12.5 Hz. Drag the sound sources to the box and view the waveforms. Which one of the sounds produced is of high quality? Why? The pure note of a tuning fork has a sine waveform and is the simplest kind of sound wave. Therefore, the sound produced by the tuning fork is of high quality. The same note on different instruments sounds different. The notes differ in quality or timbre. The difference arises because no instruments, except a tuning fork and the signal audio generator, emit a pure note, that is, of one frequency. Notes consists of a main or fundamental frequency mixed with others called overtones, which are usually weaker and have frequencies that are exact multiples of the fundamental. The number and strength of the overtones determines the quality of a note. A violin has more and stronger higher overtones than a piano. The car engine and noise has low sound quality because they do not have a fixed frequency.